called a Greco elimination. And I wanted to go over how that works if, things are still working because the iPad went to sleep. Sure. Still recording? You are. Good. Okay. So, I'm not going to do the Greco elimination on like this whole structure, but I just wanted to go over how a Greco elimination works and make sure I'm sharing that with everyone. I am. Good. Okay. So, there we go. A Greco elimination, make sure I spell this guy's name right, which I'm not going to because I can't read that small. Maybe I forgot an I. I think I forgot an I. It should be that. G-R-I-E. Because I just spelled Greco, like Greco-Roman wrestling. So with the Greco elimination, you have an alcohol, and you have, in this case I use something a little different, but you have an aromatic selenide. So you have Se, and then you have a phosphorus, a trialkyl phosphorus. In the example in the slide, it's tributyl. So from the slide, this is PBU3, but it can really be any alkyl group. It could be triphenyl, something like that. Right. So that's step one, and then step two, you have to do some sort of oxidation. So usually hydrogen peroxide, and then you'll have a base. So they use sodium hydrogen carbonate, but you use sodium bicarb, you use potassium salt, but you just need something to basically help keep it basic, and that is going to give you a double bond. So the phosphine can change, the groups on the aromatic ring can change. So in the example on the slide from the paper, they have a nitro group on their ring, but it doesn't always have to be a nitro group. Right? And so how this works is we have our selenium containing compound, and we'll use just R, right? And we have our phosphine that has some carbon groups on it, and that phosphorus is able to attack the selenium and knock off the nitrile. So we get this where we have now we'd have a selenium phosphorus bond as opposed to a selenium carbon bond. And now a phosphorus with a positive charge, we've seen this before like in a Wittig reaction. Those are oxophilic, right? Oxygens like phosphorus, particularly positively charged phosphorus. So our alcohol can add to our phosphorus. And knock off our selenium. And we can use our cyanide that we generated earlier to grab the proton off of this oxygen. This is still plus. All right, and this is going to get us to, it's kind of plus. No, not plus, sorry. Getting old. I'll go back. Olivia's still writing. No, don't be sorry. If you're still writing, 3 other people are still writing. I could just see you. So this makes me slow down. So this is fine. Okay, so it is kind of plus, it is kind of not. I'm doing this stepwise. So you're going to end up with OPR3 plus S plus R phosphorus or selenium minus, and then we make hydrogen cyanide. We could possibly get wrong. Then this attacks the oxygen, knocks that off, and we end up with a carbon selenium bond. Right, we've just done a whole lot. We just did a whole lot to replace our oxygen with the selenium. We have not in any way made a double bond yet. Right? That's where step 2 comes in. So we have to use hydrogen peroxide. Right? So this is end step 1. Right? Step 1. I'll just start a new slide with that guy. Now that we have our selenium compound, right, we have our selenium on a carbon that had the oxygen, we oxidize the selenium. We put an oxygen on it. And here's where I have to check the notes I have in my pocket here. Make sure I get the right oxidation state. It is, okay, it's just like sulfur. Cool. Right. So you're gonna have, do it right. Oh, nope. Se. Why can't I draw? Aromatic ring. And then you add your hydrogen peroxide. I'm not gonna worry about pushing arrows for this, but this is going to then oxidize your selenium. Right, to make O minus selenium plus. And then if you heat this a little, you're going to have this oxygen grab this hydrogen. These electrons come here and push electrons onto your selenium. And that makes a double bond, plus makes selenium OH. So you do all this work to put a selenium in place of your oxygen, and then you oxidize that selenium, and you're able to do a rearrangement. This is a 1,5 sigma-tripic rearrangement. Check notes again. Did I write that down? Did not. Sorry. It's a 1,5 sigma-tripic rearrangement, and it gives you your double bond. Most of the time, I will say, the reagent is what's in the slide: ortho-nitro selenium. That is the typical reagent. And again, the typical phosphorus is, again, what's in the slide: phosphorus tributylphosphine. Right. So that was a lot of work to make a double bond, right? We can't you think about ways that we learned how to make double bonds in organic 2, right, we couldn't just add like sulfuric acid to this because it's a primary alcohol, and there was other groups. Look at the slide. Right, if we use strongly acidic conditions, we have to worry about this coming off. I'm sure that this cyclopropane could open at some time, so they had to find a mild set of conditions to remove this alcohol. So if we go back to stuff, so what does, if I have TBAF, what does that do to this molecule? We'll do a whole lot of writing to change not very much. So what does TBAF do? What would H be? Bueller from Bueller's Day Off. Like when Ferris Bueller's not there, the teacher just goes Bueller. Like, someone please answer. Anyone? So what happens if? So what is TBAF a source of? Organic 2, you knew this. Organic, it's the source of the second worst grade. Not D. It's F minus. Because the worst grade is F plus. Because I could have given you a D minus and you didn't have to retake the class, but I chose to give you an F plus. Right. So this is a source of fluoride of F minus. What does fluoride do? I think I'm starting to see some of the problem with the exam. Stuff I took as like gimmies from like organic 2 were less layups and more like half court shots apparently. Yeah, you could have broke out your notes from organic 2. That would be perfectly fine. So TBAF is used to remove silicon protecting groups. So something like TBS, right? TBS is Si. Right, so TBS is tert-butyl dimethylsilyl. Right, that is the protecting group. Right, silicons really like to be bonded to oxygen. The only thing silicon likes more than oxygen is fluorine. So we put TBAF, which is a source of fluoride that won't melt your bones, in, and you'll just remove this protecting group. I am. Let me fix that. I drew the first structure since after you guys were doing that, and then I was going to fill in the second one, but I forgot to share the screen. There we go. So all this does is it removes the protecting group. So it goes from OTBS to just OH. So anything that is a source of F minus is going to do this. Anything that's going to give you fluoride in solution is going to remove a silicon from an oxygen. So, right, TMS, test, TBS, TBDPS, TIPS. These are all just different protecting groups that we can remove using fluoride. Right, now the next step, which again we're going to switch. The next step, the name kind of gives it away, right? It's a Yamaguchi esterification. sometimes known as the Yamaguchi macrolactonization, right? So this makes esters. Right? And it's a milder way to make esters than some of the ways we had learned in Organic 2, right? Where in Organic 2, right, it was like make an acid chloride out of your stuff, or or heat it with like acid. This is a milder way to do that. And it kind of illustrates, the mechanism illustrates kind of a key property of the reagent DMAP that we can go over. So we'll draw I'll let you guys draw some more stuff. We'll draw what the answer is, what I guess this is I would be, and then we'll go through the mechanism. But I will give you some time because there's a lot to draw here. I understand that. I am kind of full of regret right now as I have to draw this again, but this is the world we live in. Don't forget, if you have somehow forgot, to turn in your corrections to your exam by tomorrow at noon. After I edit my Organic 1 lecture, that will be my afternoon. So hopefully you guys will make me super happy. I'll be like, oh, this is the best afternoon ever. I just need ice cream, and I could bring ice cream. Just make it great. Okay. So this just gets really, really, really big. Okay. I'll leave drawing stuff. We're going to come back, but we'll just do this step now, since I have it drawn, hopefully. Okay. So I've got the thing that we just made right here and the structure that was given, right? So this is an esterification. So basically we're going to take the only alcohol we have and have it react with the only acid that we have and make an ester, right? So all we have to do is, again, it's really big, is have our alcohol react with our acid and hope we have enough space to draw stuff around it. We did it. Now, what's happening, right, is in this type of esterification, in most of them, right, the way the esterification works is this oxygen right here is the oxygen that ends up in the ester. So we keep our stereochemistry, right? So we don't break this bond right here, doesn't break. So since it's a wedge, it stays a wedge in the product, right? Because I'm just using that oxygen as a nucleophile. So the whole point of this, right, this activates the acid, right? So this acid chloride reacts with the carboxylic acid and then lets us do an addition. This is really bad chlorine. So I'm going to show the mechanism, but I'm going to show it on a much smaller molecule, so I have to draw this 18 times or whatever. Fair? Okay. So if you have your alcohol, you have your acid, your acid, and then you have your acid chloride for your Yamaguchi. All right, so if you remember the nucleophilic oxygen of a carboxylic acid is the one that is double bonded to the carbon. So what happens is these electrons here will push down and push these electrons out to add to the acid chloride. This is your friend from Organic 2. If I spelled that right, tetrahedral intermediate. Right? This falls apart. Bloop. Bloop. And we get here. It's going to end up going on the next page. But now your triethylamine can act as a base and grab your extra proton. I lost the carbon. No, I didn't. Okay. All right, so that's going to end up making. Give a second. Get off of there. Yes, I was inordinately happy that the baby rolled over yesterday. I was like, oh man, look at the baby. I feel like he's quickly leveling up and will soon like surpass me. I guess, but I didn't expect to be surpassed like, when I was like only 40. Figured like later on, fine, like I could get used to being surpassed, but like now I'm just like, oh man. So I just hope like he can't have a brother because like the one of Menendez brother situation. That is a deep cut. You guys are probably too young to get that reference. They're identical twins who shot and killed their parents. Like they were rich, that was like a big deal, and then like it was on the news a lot. Yeah. You're like, oh yeah, I remember kids who murdered their parents. Yes, that's right. My wheelhouse of things to remember. Yes, I'm like, no, I don't want to be replaced that hard. Like you can send me to a home, like send me to a nice home in Florida, but don't like murder me. All right. So do you remember what this functional group is called? It's like you took two acids and you took water out of them. So instead of being hydrated, they're not hydrated, they're anhydride. So there's an anhydride, two acids stuck together, and you just pulled water out. Right? So now I have this anhydride, and you can have your alcohol add to your anhydride. Well, no, not quite yet. We got ahead of the game here. Okay. So this is where DMAP comes in. Let's forget, this is like the most important part. All right, so the dimethylamine, the dimethylamino, that is just the N with the two methyl groups on it. And the pyridine is the rest of the ring. And DMAP gets to do two things in its life. One, it can be a base. Right? It has two nitrogens that have lone pairs, it can be a base. But the other thing that it does a lot, especially with like if there's an acid chloride around or an anhydride around, is it will add to a carbonyl carbon. So the nitrogen of the pyridine, that lone pair, isn't tied up in resonance, and it's able to go add to stuff. And what this does is, other than not fit easily on my iPad screen, is when this adds, your molecule can then spit out the other side of the anhydride, and you get, there's a plus here, this activated carbonyl. Or did I miss this step? Because they don't have any of their TBS groups on anymore. You have to go check that out in a sec. And so now what you end up with is you get DMAP, positively charged, on your carbonyl carbon, plus you have your anion that you spat out. So this DMAP that is now stuck to your carbonyl carbon is a really, really, really good leaving group. Right? There's no lone pair on that nitrogen now. Right? That lone pair is being used to make a bond. So there's no interaction with the acetyl bond O. So you just got this positively charged thing hanging off your carbonyl carbon that pulls electrons away from the carbonyl carbon that makes it more positive and is a good leaving group. So now, if you had thought ahead, you could have your alcohol add to your carbonyl carbon. Right, and then that'll give you, again, your friend tetrahedral intermediate. Electrons come down, push out nitrogen. This gives you this guy plus DMAP. And then you could have another triethylamine or other base. Come grab that extra proton and give you your ester. So this is a good way to make esters. It also is used a lot to make lactones. So depending on where you see the name, here, like I said, in the slides, I have this Yamaguchi macrolactonization. In my like name reaction book, sorry, I have a Yamaguchi esterification. In my name reaction book, it's Yamaguchi macrolactonization. So where this is used a lot, in addition to just making, to bringing an acid and an alcohol together to make an ester, is let's say you have an acid and you have I absolutely do not mind going back. This should be plus 3. Much better. Cool. Okay. So what this is used for a lot is if you have an acid and then you have a lot of carbons, 10, 15, 20 carbons between that acid and the alcohol, you use your Yamaguchi conditions. Yamaguchi, right? And that will make a lactone. Still. Lots of carbons. Right? So you don't have to use. So this is a way to have your acid and your alcohol and then close the ring. Usually you'll run this at a low concentration. Right? Because your goal is to only ever have your alcohol run into the activated acid in the same molecule. So you run it really, 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 really dilute, so that if you, so that the chances of it running into another molecule are really low. I really wish that, well, I guess I don't have to redraw it. I'm going to go back so I don't have to redraw something. All right, so we all established that this was I, correct? And if we go look at our slides again, right, we did the esterification, and this was I. Cool. I didn't have to redraw it. It's too big. Right. The next step is they use a Grubbs catalyst, and they put these two, right? They put this carbon of this double bond and this carbon of this double bond. They put them together to close the ring and make that double bond there. Now, I'm going to have to redraw some stuff. They use Lindlar's catalyst in H2, and they actually talk about in the paper that any other conditions they use to try to hydrogenate this double bond hydrogenated this cyclopropane instead. So I know that Lindlar's catalyst usually takes an alkyne and turns it into a cis-alkene. But they had to mess around and use it to get rid of this double bond. So basically, J is just the big ring. So J would be, I'm going to draw it the same way I have it drawn here, is just basically this compound without the double bond. Right? So While Lidlar's catalysts, like I said, most of the time just reacts with alkynes, they were able to mess with the conditions, change the pressure and whatnot to get it to do this particular reduction. So it was not normal. Now, what I wanted to check is, I feel like I must have forgot a step. Never would have happened. It can't be right. I would ever mess up. But all the protecting groups are off of their alcohols, right? So somewhere in the esterification or the Grubbs reaction, we lost our protecting groups. And so I don't know if I forgot a reagent somewhere, like a step 2. But let me check real quick. I'm going to stop sharing for a second. Sorry, Zoom. I get out of here so I can actually get stuff. I'm going to look at this with the paper and make sure and see what happened to those things so I can tell you, the people. Nope, it's just I'm bad. So, I just did a bad job drawing my structures. So let's fix that. Because I specifically do it later. Did I put them back on? No. Okay. I know what happened. All right, both these alcohols still have their protecting group on them. I just stroked out. So let me share my screen so you can see what I did. Let me share my screen so you can see what I did. If I say it enough times, it'll actually happen, and I won't have to do anything. Right? So those 2 alcohols still have their protecting group. So I just, when I copied the structure, I just lost the protecting groups. Sorry. Okay. So we got that guy. That is our J. Nope. Zoom school sucks. So much more work. Hey Zoom, why did you... And I say that, and Zoom heard me, and then Zoom moved my controls onto the projector screen so I can't see them. Zoom was like, oh, I suck, do I? I'll show you. Okay. Hey, we did it. Cool. So, we have our J. Right? And then they use iron trichloride and water, and they remove the TBS groups, plus they remove the acetal. So this is, again, kind of a non-standard use of a reagent, right? So do you guys remember how acetals come off? What you have to do to get an acetal off? You have to add water. So we got that part. But what do you have? You have to usually use acid or something that will protonate or bond to the oxygens of the acetal, right? So instead of using sulfuric acid or something like that, we kind of did it. They used iron. So all you really need to do for an acetal, right, is you need to have something. We're going to call this a Lewis acid, right? Just anything that the electrons on the oxygen can donate to make it positive. Because then that starts the reaction where then this lone pair pushes that out. And it starts us on our way to where we can get to this. Oh my god. Am I drawing? I've been drawing so much. It's awful. I'm sorry. I'm like talking about stuff and I'm like halfway through drawing things. So this is the product, which is already up there, poorly scribbled. Right? But, so for an acetal to come off, you need to have some Lewis acid or just H+, right? And you have to let your oxygen bond to that thing to make the oxygen positive. And then that allows the acetal to open, and then you get to this guy. And this is then what you add water to. Right? So instead of using a proton, instead of using just H+, they used iron trichloride, and that allowed them to remove both the both the acetal to get to the ketone that they wanted right here. Right, so this becomes ketone, and it let them take off the TBS groups all in one go. But they just needed something that they could have that would bond to the oxygens of the acetal. And there's a lot of stuff going on in this molecule, right? There's an ester, right? We've got an ester, we've got a ketone, we've got an acetal, we've got the protected oxygens. So they had to find something that would react with the acetal but not mess up their ester or their ketone or change anything else about the molecule. Right, so they find that iron trichloride would bond to that, let it open up, and then once you get here, right, this is the point where your water starts to add to get from acetal back to carbonyl. So the next step, if you want to save yourself some drawing, is what they figured out was they couldn't get the acetal off and keep the TBS groups on. But they couldn't do this next step, the step to make L, which we all know what this is, right? What kind of reaction is this? Oh, wait, no, of course. Not showing that screen. Oh, my life is pain. Great. Okay. So, share. Command it. Share. Do it. Yeah. Okay. So, they couldn't take out the acetal and leave the oxygens protected, but they couldn't do this step. What is this step? We're going to add base to it. I forgot the base. We're going to add a base. We're going to make a phosphorus double bond to a carbon. Begins with a W, but because it's a German guy's name, it's somehow said with a little bit of a V. Wittig, yes. Yes. So we're going to do a Wittig reaction. But they couldn't do the Wittig reaction with the free alcohols. So they added the smallest possible protecting group, TMS, to these two oxygens. So basically, K is just re-protecting these to get rid of the OHs and have O silicons in their place. So, right, they just go, I'm going to draw this one more time. Sure, is this the best use of my time? I don't know. My hope is that you learned some stuff. Doing a good job. That's all I want out of my life. I guess that and the baby not to murder me, but, you know, or go to jail. I don't want the baby to go to jail. Right, so this would be K. Cool. So then we have tributyl phosphorus. Clearly I forgot the base, but we'll just write base. Fine. Plus we've got Cl minus, and we'll add a base. And I'm probably not going to draw out the whole thing, right? But, so what happens to this when I add a base to it? So the base is to react with this salt. So what is the point of that base? He said to the people that are literally doing this reaction next week. Not this little reaction, but this step. In lab themselves. Literally. Alright. So, right, you add base to this. A Wittig reagent, right, looks like this. It's a phosphorus double bonded to a carbon, right? Right now, my phosphorus isn't double bonded to the carbon. There are still two hydrogens here. So you add base to get to make that carbon phosphorus double bond. And then they do a Wittig reaction with this. So, there are 3 different carbonyls in this molecule, right? There's the blue one, the green one, and the orange one. And they only do this Wittig reaction with the blue carbonyl. They don't do it with the green one or the orange one. Why do you think they only do it with the blue one? The blue one is more accessible, right? So comparing blue and orange, the orange one has 2 methyl groups and then a methyl group over here, right? So it's pretty buried. It has a lot of stuff around it that makes it hard to get to, right? The green one is the carbonyl of an ester, and esters are less reactive than ketones. So that's why we don't react with the green carbonyl, because it's an ester carbonyl, and they're not super reactive. So, the only one that you can really react with is the blue one. It's only got a methyl group on the one side, right? So not nearly as crowded as the orange one. And the other side is branched, but this is kind of equivalent to having a methyl group there. So it's much easier to get to, So we're just going to maybe not draw the whole thing. Right? We're going to just turn that blue carbonyl from the previous page into a double bond. Oops, and I moved my carbons around a bit. S. And there we go. Make sure I drew it right on the previous page. Don't yell at me. He did not. This should be this. I'm sorry. I like what? Okay. One sec. I drew it two different ways on the slide because I'm slowly coming to the realization that I'm bad at my job. Let's see how it's supposed to be. It is supposed to be. Aha. I will fix it. I drew it right one way and then wrong the other. So I'll fix it and then give you guys time to fix it, and you can just silently or audibly shake your head at me. But if your head audibly shakes, it's probably a problem. Just saying. Not that kind of doctor, but... Okay. Fixed. Fixed. Didn't fix the slide, but I at least fixed the drawing, which is, half the battle. One sec. Oh, no, I can do it this way. Here, buddy. There you go. Okay. So, I was right on the first slide, wrong on the right on the first structure, wrong on the second. So it's carbon bonded to sulfur, which I think is what I drew for the first one. But then the product is off. But nonetheless, cool. This should look like this. Sulfur, then carbon, and no. What is wrong with me? 1, 2, 3, 4. I give up. I'm retiring. I'm like illiterate or something now. It's terrible. He was right the whole time. It was just the friends you make along the way. I don't know. All right. What'd you give this guy? Sorry, that was a little bit of a rocky road there at the end. But going through all of this synthesis, right? You have seen or been introduced to, or have a fleeting memory of, most of the reactions and steps that were used to make this molecule. Right? So if we look at, what was that? All right. You know what methyl lithium does to an ester. You know what a Horner-Wadsworth Emmons reagent does. Right? You know what DMP does. It was a little tricky to get there. Right? You know how to reduce an ester to an alcohol. You know what Swern does. You know what a Wittig reagent does. You know what Diboll does. You didn't know this one. I didn't know this one. I had to look this one up. Right. You learned a new reaction, a new way to make a double bond. Right? Even if you didn't like have Greco in your head, you knew ways that you could turn that alcohol into a double bond. Right? Deep down, somewhere in your heart, I know that you know what TBEF does. So we're going to give you a win on that one, that you know that one as well. Right? This one was new, right? But it was just a way to make an ester. And maybe, again, you don't know this way to make an ester, but you know a way to make an ester, right? So just like we talked about before, sometimes, right, the way you think of something working could be reasonable, right? But then when you go to try it, it might not work. So you have to try other things. But like when you are coming up with a synthesis, you're trying to like pick something, like when you're proposing a synthesis. When you're proposing a synthesis, like you have to do this semester, right? You're trying to say, hey, I am picking something that I think will work because of these these other people had something similar to what I did, and they said theirs worked, right? So then, but you don't know for sure until you actually do it on your molecule, right? So you're coming up with your best supported guess for what that reagent would be. So right, so if you said I'm just going to make an acid chloride, right? Right, if you could find a bunch of references that say like, hey, for a molecule this complicated, using these reagents is fine. Cool, right? But you wouldn't know like, oh wait, no, that doesn't work really well. I need to find something else until you actually start doing the reactions. So a lot of times, like this Lindlar's catalyst thing, this was not, I'm willing to bet, the first, second, or like 15th thing they tried. Right? They probably just kept going through stuff until they got to Lindlar's catalyst working. Right? But you know something similar to this. You know what Grubbs does, so that gets you here. This one, admittedly an oddball. And then you didn't know this, but you know what a vinegar agent did. And then the last step here, the citric acid, it just TMS groups aren't very stable, so they just add a little bit of acid, and that knocks off those TMS groups that you put on before to get to the actual product that they wanted. And so the way they did this synthesis was they had this ketone here, and so they wanted to see what happens if you change this ring. So they actually did this, what's it called? They did this Wittig reaction like 5 times with different rings. So like the last thing they did was they just put on a different ring so they could go see if changing the ring led to a different biological activity. Because they were interested in making the molecule, but they wanted to make it in such a way that they could change this last group at the end. One second. I'm drawing, but I'm going to show it to you in a second. So if you wanted to make 1 enantiomer of that, sorry. I was trying to make it bigger for Olivia, and I just like Made it all go away for her. Aha, much better. If you wanted to make one enantiomer of that, how would you do it? A sharpless epoxidation. So, of course, I don't remember everything that is involved with that, so I'm going to cheat and go back. Right. Right, so it's a sharpless epoxidation. Right, and that means you have to use titanium tetraisopropoxy, a ligand. We're going to say plus. It could equally be minus. Right? And that's it. So, I'm missing something? I'm missing something. Oh, that's right. And tert-butyl hydrogen peroxide. So, tert-butyl hydrogen peroxide is TBHP. Gotta fix that N. How would I do that? Everyone furiously flipping their notes, thinking, need to add an amine and alcohol. And it would make, you can make both the alcohol and the amine chiral, but I'm only making one chiral center here. So I'm only worrying about the amine. Yeah. A lot of sharpless stuff. He was very good at this. All right, so you have to have your amine with your, it is going to be a sodium salt with a chlorine on it, right? And then you need to add, get this right here, and you need to add osmium. It's very similar to osmium tetroxide, except less eyeball sticky. So you add your amine source, you add your oxygen source, right? Your osmium, this is osmic acid, or potassium osmolate. And then you need a ligand. And the ligands for these are these HQD to, like, I'm looking at one that's just AQN. But there are a bunch of different ligands that are similar, right? That are these big, right? There are these big structures here. I don't expect you to like remember them, like remember the structures, but they're like big things like this, right? This is the FAL, I do believe, right? So you just have big ligand, right? That is chiral, right? So even though this stuff's a little different, right? At the end of it, it's, hey, how do I know how to make something that looks like this, right? And then what do I need to start with, or what are the reagents I need to do that? So like that part of it from like organic 1 to organic 2 really hasn't changed. So the last thing that's new here is, you know what? You were good sports. So we'll save this last slide in the end part for Tuesday, and then we'll do, I'll put up some slides about addition to carbonyls, how you predict if you're going to make the R and S enantiomer when you add to a carbonyl based on the chiral centers around the carbonyl and how you predict that. And then I will probably throw together maybe I'll find another synthesis to go through and try to, that's going to like reinforce stuff that you guys have done and maybe introduce a new reaction or two. And then that'll be probably next week. And I owe Olivia candy because she came to class on like reverse Halloween day. So I owe her some candy, which I'll go to my office and then throw at her. We'll maintain social distance. All right. Thank you, everyone. I will see half of you at like 2 o'clock. The other half I'll see Tuesday. Coastal is still open. We won't have class? We don't have class on Tuesday? Okay, that's cool. We did. Yeah, yeah, so we should still have class. I mean, do you guys want to go? Are you guys all going to vote? Okay. I mean, we could not have class on Tuesday. Like, that's just less slides for me to make.
I texted Shop 111. The official statement is that Coastal doesn't have class on Tuesday.
So the official statement we got from HR is that we're not closed. So I guess I don't know. Let us.
I mean, I assume that campus would still be open, but just without classes going on.
Okay. I thought about canceling class. Screw it, no class on Tuesday. Yay! Go vote for someone that you like. Not being political in any way. Go vote for someone you like.